Ancient rooftops reveals roof-based movement through mudbrick house clusters, showing streets were unnecessary while avoiding alien stories. Layered mounds reveals deep occupation history through archaeological soil bands, showing time became vertical while avoiding alien claims. Packed houses reveals wall-to-wall through dense housing blocks, showing density-shaped planning while avoiding alien ideas. Streetless pathways reveals elevated social routes through flat roof surfaces, showing neighbors crossed ceilings while avoiding alien legends.
Roof hatches reveals vertical home access through square ceiling holes, showing rooms opened upward while avoiding alien assumptions.
Smoke vents reveal hearth ventilation logic through upward smoke paths, showing smoke-shaped design while avoiding alien narratives. Honeycomb neighborhoods reveals missing street grids through joined domestic walls, showing order looked unfamiliar while avoiding alien theories. Descending ladders reveals ceiling entry systems through timber ladder routes, showing thresholds faced skyward while avoiding alien shortcuts. Joined dwellings reveals compact settlement cells through interlocking room plans, showing homes formed networks while avoiding magic stories.
Wild Travelers reveals learned rooftop navigation through adult guidance patterns, showing routes were taught while avoiding magic claims.
Excavated layers reveals material movement evidence through post-hole plaster clues, showing movement was inferred while avoiding magic ideas. Single openings reveals unusual urban order through settlement-scale views, showing cities varied early while avoiding magic legends. Interior ladders reveals hearth-side entries through oven wall placement, showing entry-shaped rooms while avoiding magic assumptions. Raised platforms reveals platform activity zones through edge platform arrangements, showing floors organized life while avoiding magic narratives. Side compartments reveals household storage habits through low side openings, showing storage-structured homes while avoiding magic theories. Repeated plans reveals shared building traditions through parallel house layouts, showing traditions-guided builders while avoiding magic shortcuts. Mudbrick surfaces reveals repairable living architecture through smooth plaster coatings, showing maintenance-sustained homes while avoiding modern stories. Walkable ceilings reveal roof infrastructure rolls through reed beam layers, showing ceilings carried people while avoiding modern claims. Shared shafts reveals multi-purpose roof openings through light smoke access, showing design-solved needs while avoiding modern ideas. Roof repairs reveals maintained public surfaces through weathered roof paths, showing roofs required care while avoiding modern legends. Plaster renewals reveals thin temporal layers through replastered floor films, showing surfaces recorded time while avoiding modern assumptions. Filled rooms reveals foundation reuse cycles through deliberate room filling, showing old rooms supported while avoiding modern narratives. Growing mounds reveals vertical settlement growth through stacked architectural remains, showing mounds grew upward while avoiding modern theories. Buried phases reveals buried domestic sequences through downward excavation reading, showing history lies below while avoiding modern shortcuts. Rare doorways reveals limited side access through scarce lateral thresholds, showing doors were uncommon while avoiding royal stories. Private walls reveals interior privacy patterns through roof shared circulation, showing privacy coexisted socially while avoiding royal claims. Changing clusters reveals gradual neighborhood shifts through successive building adjustments, showing plans change slowly while avoiding royal ideas. Moving architecture reveals people-room relationships through animated cutaway views, showing architecture needed movement while avoiding royal legends. Grain baskets reveal stored food routines through hearth storage scenes, showing food-anchored households while avoiding royal assumptions. Obsidian tools reveals volcanic craft networks through dark glass flakes, showing craft reached outward while avoiding royal narratives. Woven platforms reveals multi-purpose sleeping areas through mat-covered platforms, showing rooms served flexibly while avoiding royal theories. Heated clay reveals domestic heating choices through heated clay balls, showing technology stayed domestic while avoiding royal shortcuts.
Food rains reveals activity zone patterns through bone seed scatter, showing work-left patterns while avoiding mythic stories.
Clean interiors reveals organized refuse disposal through external midden deposits, showing cleanliness-required systems while avoiding mythic claims. Plaster labor reveals architectural maintenance work through family repair gestures, showing labor-renewed houses while avoiding mythic ideas. Worn ladders reveals daily passage traces through polished ladder surfaces, showing use-marked wood while avoiding mythic legends. Overhead sunlight reveals illumination from above through bright hatch geometry, showing light-structured interiors while avoiding mythic assumptions.
Smoke stains reveals ventilation problems inside through blackened roof margins, showing smoke-left evidence while avoiding mythic narratives.
Storage rooms reveals protected household goods through small storage spaces, showing storage-protected resources while avoiding mythic theories. Pattern seals reveals non-written pattern making through soft clay impressions, showing symbols stayed non-writing while avoiding mythic shortcuts. Flexible rooms reveals overlapping domestic functions through limited room footprints, showing space stayed adaptable while avoiding sensational claims. Symbolic homes reveals symbolic domestic space through decorated buried floors, showing meaning shared rooms while avoiding sensational ideas. House memories reveals accumulated household memory through repaired painted walls, showing memory accumulated materially while avoiding sensational legends. Rooftop exchange reveals neighborly roof contact through basket passing gestures, showing neighbors interacted visibly while avoiding sensational assumptions. Shared ceilings reveals community overhead routes through linked private rooms, showing community moved overhead while avoiding sensational narratives. Painted fragments reveals fragmentary artistic choices through ochre black shapes, showing art survives partially while avoiding sensational theories. Full reliefs reveals plaster animal power through projecting horn forms, showing wildness entered homes while avoiding sensational shortcuts. Animal murals reveals painted animal motion through wall painting remains, showing walls carried stories while avoiding fantasy stories. Leopard figures reveals ambiguous leopard imagery through paired animal motifs, showing the meaning remains debated while avoiding fantasy claims. Red pigments reveals pigment preparation labor through stone grinding tools, showing art required labor while avoiding fantasy ideas. Hidden images reveals covered older artworks through fresh plaster skins, showing walls hid histories while avoiding fantasy legends. Decoration layers reveal changing decoration sequences through peeled wall sections, showing decoration changed repeatedly while avoiding fantasy assumptions. Horn installations reveals constructed horn features through crafted plaster supports, showing features were handmade while avoiding fantasy narratives.
Wild symbols reveals interior symbolic worlds through household image placement, showing symbols live domestically while avoiding fantasy theories.
Clay figurines reveals domestic figurine contexts through small clay objects, showing certainty stays limited while avoiding fantasy shortcuts.
Buried bodies reveals interpretive shape variation through contrasting figurine silhouettes, showing meaning stays plural while avoiding fictional stories.
Evidence fragments reveals partial puzzle pieces through transparent evidence levels, showing interpretation needs caution while avoiding fictional claims. Room gatherings reveals non-monumental ritual possibilities through decorated room gatherings, showing temples remain unproven while avoiding fictional ideas. Landscape animals reveals wild interior links through animal landscape echoes, showing wild worlds mattered while avoiding fictional legends.
Broken scenes reveals incomplete narrative fragments through damaged plaster pieces, showing absence changes readings while avoiding fictional assumptions.
Living plaster reveals renewed wall surfaces through successive renewal layers, showing walls stored memory while avoiding fictional narratives. Leaf shadows reveals hearth-lit relief effects through flickering fire shadows, showing reliefs felt present while avoiding fictional theories. Cautious archaeology reveals fragment-based narratives through context comparison dating, showing claims need evidence while avoiding fictional shortcuts. House art reveals rich household imagery through domestic art contexts, showing houses carried richness while avoiding impossible stories. Decorated walls reveals integrated visual architecture through wall platform merges, showing surfaces work together while avoiding impossible claims. Horn silhouettes reveals burial evidence transitions through horn shape matching, showing mortuary evidence emerges while avoiding impossible ideas. Floor burials reveals platform burial practices through cutaway floor lifts, showing homes held dead while avoiding impossible legends. Buried ancestors reveals underfloor household memory through sealed platform surfaces, showing memory stayed nearby while avoiding impossible assumptions. Layered interments reveals repeated mortuary deposits through layered skeleton placements, showing burials accumulated slowly while avoiding impossible narratives. Careful brushing reveals human remains evidence through brush-cleaned bones, showing care replaced treasure while avoiding impossible theories. Sealed bodies reveals resumed domestic life through new plaster coverage, showing life resumed above while avoiding impossible shortcuts. Reopened graves reveals secondary bone practices through reopened burial cuts, showing death remained complex while avoiding anachronistic stories. Beaded remains reveals mortuary material traces through beads bones plaster, showing materials-shaped interpretation while avoiding anachronistic claims. House histories reveals variable remembrance patterns through room rebuilding sequences, showing memory varied locally while avoiding anachronistic ideas. Special houses reveals possible special roles through decorated rebuilt houses, showing roles remain uncertain while avoiding anachronistic legends. Missing palaces reveals non-elite settlement patterns through absence visualization panels, showing kings stay absent while avoiding anachronistic assumptions. Odd variation reveals uneven household goods through household comparison sets, showing hierarchy looks limited while avoiding anachronistic narratives. Roof clusters reveals social proximity routes through roofline neighborhood lights, showing neighbors lived closely while avoiding anachronistic shortcuts. Object links reveals household relationship clues through matching object groups, showing relationships leave traces while resisting alien stories. Kinship circles reveals overlapping social ties through abstract relation circles, showing families remain uncertain while resisting alien claims. Silent evidence reveals lost personal voices through blank identity spaces, showing people stay anonymous while resisting alien ideas. Plaster footprints reveal brief human traces through preserved plaster marks, showing individuals briefly appear while resisting alien assumptions. Generational layers reveals stacked lifetime evidence through floors, walls, burials, showing generations overlapped materially while resisting alien narratives. Houses reveals shelter as archive through layered house remains, showing houses stored lives while resisting alien theories. Closed platforms reveals whole settlement focus through closed floor sections, showing mound-scale returns while resisting magic stories. Slow excavation reveals context-preserving methods through trowel brushwork, showing context comes first while resisting magic claims. Charcoal samples reveals dated hearth remains through sample collection gestures, showing fire's dated phases while resisting magic ideas. Radiocarbon anchors reveals chronological scientific control through shrinking charcoal forms, showing dates need samples while resisting magic legends. Stacked strata reveals building phase order through soil band sequences, showing time stacks visibly while resisting magic assumptions. Animal bones reveals dietary animal choices through sorted bone shapes, showing meals become evidence while resisting magic narratives. Obsidian roots reveals exchange landscape connections through moving stone paths, showing exchange extended landscapes while resisting magic shortcuts. Volcanic glass reveals geological tool origins through distant volcano forms, showing tools had sources while resisting modern stories. Fragile plaster reveals serious conservation vulnerability through protective cover panels, showing exposure damages evidence while resisting modern claims. Protected paintings reveals surface preservation risks through careful stabilizing brushwork, showing discovery needs care while resisting modern ideas. Parent models reveals uncertainty-aware reconstruction through transparent overlay houses, showing models remain provisional while resisting modern legends. Repeat hypotheses reveals multiple explanatory models through overlapping house diagrams, showing hypotheses can compete while resisting modern assumptions. Patient digging reveals careful field practice through recorded trench squares, showing speed risks context while resisting modern narratives. Archive trays reveals organized evidence fragments through fragment storage trays, showing fragments need provenience while resisting modern theories. Plan comparisons reveal long-term continuities through layered house maps, showing patterns shifted gradually while resisting modern shortcuts. Material dating reveals pre-literate dating methods through material association chains, showing writing was absent while resisting royal stories. Visitor walkways reveals protected fragile surfaces through elevated viewing paths, showing visitors keep distance while resisting royal claims. Shelter shadows reveals modern conservation choices through large protective roofs, showing preservation is active while resisting royal ideas. Dense living reveals pre-street settlement density through farming herding crafts, showing complexity emerged early while resisting royal legends. Urban complexity reveals complexity without rulers through ordinary house evidence, showing urbanism had alternatives while resisting royal assumptions. Rooftop logic reveals circulation through roofs through roof path diagrams, showing roofs organized circulation while resisting royal narratives. Occupation timelines reveal rebuilding abandonment preservation through mound timeline bands, showing settlements become archives while resisting royal theories. Later comparisons reveals different urban templates through fading later cities, showing cities differed widely while resisting royal shortcuts. Ancient innovation reveals practical mudbrick design through non-mythic construction scenes, showing innovation was human while resisting mythic stories. Breathing houses reveals roof hole ventilation through smoke ladder shafts, showing houses needed airflow while resisting mythic claims. Visible uncertainty reveals honest missing evidence through unfinished reconstruction edges, showing reconstructions stay cautious while resisting mythic ideas. Connected systems reveals integrated settlement story through art burial architecture, showing systems interlock deeply while resisting mythic legends. Quiet mounds reveals buried crowded worlds through transparent house glows, showing ruins hide life while resisting mythic assumptions. Respectful reconstruction reveals evidence-based fading through ruin reconstruction transition, showing evidence remains central while resisting mythic narratives. Dusk rooftops reveals looped roof movement through darkening roof hatches, showing story circles back while resisting mythic theories. Hidden beginnings reveals concealed mound beginnings through sunrise soil outlines, showing mounds invite excavation while resisting mythic shortcuts.
This South American fish can activate another animal's muscles without touching it, using electricity generated inside its own body.
Electric eels inhabit slow rivers, floodplains, and seasonally changing waters across northern South America, especially within quiet backwaters.
The habitats are dark, cluttered, and difficult to search visually, making electrical sensing far more useful than eyesight.
Electric sensing turns murky water into a readable electrical landscape. The advantage matters during dark water navigation.
Despite its common name, an electric eel is a South American knife fish rather than a true eel.
A long anal fin provides smooth forward, backward, and hovering movement, while the elongated body remains nearly straight. Precise hovering keeps the sensory field aimed steadily, while the animal investigates prey hidden among roots and leaf litter.
Electric eels regularly reach the surface because atmospheric air supplies most of the oxygen supporting their metabolism.
A highly vascular mouth lining absorbs oxygen after every surface gulp. Control strengthens during fast predator escape. Air breathing permits survival in stagnant pools, where dissolved oxygen can fall below levels tolerated by many fishes. Most of the elongated body behind the vital organs contains specialized tissues devoted to generating electrical discharges.
Electrocytes are specialized cells arranged so their tiny voltages add together. That helps during muscle cell transformation.
Evolution transformed muscle-derived cells by reducing contraction, expanding membrane specialization, and coordinating their electrical activation together. Asymmetric nerve input lets each electrocyte create a directional voltage difference. Control strengthens during synchronized neural firing. A neural command opens ion channels almost simultaneously across the organ. Efficiency rises during sodium channel opening. Each activated cell contributes only a small electrical potential. Thousands combine to create the organ's full voltage.
Series arrangement adds the tiny voltage from each cell, producing a much larger discharge across the complete organ.
Parallel arrangement increases available current, while series arrangement raises total voltage. That helps during parallel current amplification.
Surrounding water completes the external circuit whenever a high voltage pulse travels from the eel toward another animal.
Genetic and anatomical evidence now separates electric eels into 3 living species, notably during species-level divergence. Each recognized species occupies a different combination of regional geology, water conductivity, and evolutionary history across Greater Amazonia. Electrical performance changes with the conductivity of surrounding water. Conductivity reshapes both current pathways and target exposure. Water chemistry reshapes the current pathway, changing how strongly a discharge crosses prey, predators, and surrounding habitat. Voltage alone cannot describe the biological effect of an electric discharge. Performance improves during multi-factor electrical effects.
Current, pulse duration, conductivity, and contact geometry together determine the biological effect of any electrical discharge underwater.
During a powerful pulse, the eel's head and tail behave as opposite electrical poles within the surrounding water.
Body position lets the animal shape where the strongest current travels. Precision increases during body position control.
Weaker pulses serve continuous sensing and communication, while powerful volleys are reserved mainly for predation and defense.
Objects with different conductivity distort the eel's self-generated field, allowing nearby structures to be detected without vision. Electroreceptors distributed across the skin sample tiny field changes created by nearby objects, prey, and environmental boundaries.
Electrical distortions become spatial information inside the nervous system. That neural map guides movement through cluttered darkness.
Active electrolocation reveals obstacles even when vision contributes almost nothing. The advantage matters during obstacle shape reconstruction. Living prey produces a distinctive electrical signature compared with stones, wood, sediment, and empty surrounding water nearby. Movement changes the pattern repeatedly, helping the eel separate prey from static background clutter during prey tracking. Pulse timing can change with context, arousal, and nearby electrical information. That helps during context-dependent pulsing. Weak electric discharges also carry social information between individuals without triggering a predatory or defensive attack underwater. Electrical signals can help distinguish species, individuals, and behavioral states. Performance improves markedly during species signal recognition.
After detecting prey, the electrical system rapidly shifts from environmental mapping toward high-voltage muscular control instantly.
A hunting eel can activate nearby prey motor neurons remotely, forcing muscles to respond before physical contact occurs. The prey's own nervous system carries the eel's externally imposed command. This matters during prey nerve firing. High-frequency volleys force simultaneous contraction across the prey's body, producing a brief period of whole-body muscular tetanus. A temporary tetanus blocks coordinated escape during the eel's final approach through cluttered, low-visibility habitat underwater.
Controlled experiments reproduce the same muscular response by applying eel-like electrical stimulation directly to isolated prey preparations.
Closely spaced pulses prevent full relaxation between twitches, merging separate contractions into one sustained, forceful muscular response.
Prey becomes immobilized because its own nerves and muscles obey externally imposed electrical stimulation from the eel.
Electricity does not physically push the target. Instead, it recruits the target's motor neurons and muscle fibers.
External voltage crosses the threshold needed to initiate action potentials. That becomes valuable during motor threshold crossing. Neural activation closes the timing gap between detection and capture. Control remains useful during rapid neural conduction.
A sudden high-voltage burst can interrupt an escape turn before the prey completes the movement or accelerates away. Immobilization creates a short capture window, allowing the eel to close distance before coordinated swimming can resume.
Curling positions both electrical poles near the target. This bioelectric mechanism remains important during opposite pole positioning.
This posture greatly increases current through the prey's body. Curling therefore amplifies stimulation without raising internal output.
Curling strengthens stimulation through geometry, increasing current across the prey without raising the organ's internal voltage further.
Repeated volleys keep struggling prey from regaining coordinated movement. Continued stimulation preserves the eel's brief capture advantage. High-voltage hunting carries a metabolic and electrical cost. Recovery between attacks restores ion gradients across electrocyte membranes.
Between attacks, membrane pumps rebuild sodium and potassium gradients across thousands of electrocytes inside the electric organs.
Recharge depends on active transport, resetting thousands of biological battery cells. This matters during ion pump resetting. When prey remains hidden, the eel emits brief electrical doublets that can force an involuntary muscle twitch from concealment. That twitch moves leaves, sediment, or water, revealing the hidden animal against an otherwise motionless underwater background.
Laboratory doublets reproduce the same rapid muscular twitch observed when eels searched naturally for concealed prey underwater. Spacing between two pulses is well suited to summating the prey's muscle response into one detectable movement.
After delivering a doublet, the predator pauses briefly and monitors the surrounding electric field for nearby motion. Electrolocation converts the involuntary twitch into a precise positional clue. This remains important during twitch signal detection. Multiple viewpoints improve localization inside cluttered cover. That electrical strategy provides major advantages during multi-angle localization. Movement distinguishes living prey from inert debris more reliably than static electrical shape within cluttered underwater habitat. Once the target is located, the eel immediately replaces probing doublets with an immobilizing high-voltage volley. The same bioelectric system first exposes concealed prey. then prevents that prey from escaping the approaching predator. A complete hunt combines weak electrolocation, forced twitching, high-voltage immobilization, body curling, and rapid physical capture. Low-voltage discharges continuously refresh the eel's environmental map before any predatory strike becomes necessary inside cluttered water. An initial field distortion suggests a possible living target, but cannot confirm identity without additional testing underwater. A doublet challenges the hidden object to respond biologically. Any twitch separates living prey from motionless environmental clutter. The resulting motion confirms that excitable tissue is present. The eel immediately converts confirmation into precise targeting. Twitch geometry helps aim the following high-voltage strike. A clearer orientation strengthens the following immobilizing volley.
The attack volley recruits the prey's own motor system, turning ordinary muscle physiology into a temporary restraint.
Electrical control reduces the need for a prolonged physical chase. This remains important during rapid target capture.
Bioelectric hunting becomes especially valuable where darkness, roots, and sediment make ordinary visual pursuits slow or unreliable.
After feeding, the animal returns to low-voltage sensing rather than maintaining energetically costly attack volleys afterward. Electric eels also direct powerful volleys toward large nearby threats that cannot be treated as ordinary prey. During shallow water defense, an eel may approach vertically and rise toward the intruder instead of retreating. Pressing the chin against a conductive target creates a more effective pathway for electrical current through the threat.
As the eel climbs higher from the water, measured current entering the contacted object rises progressively and dramatically.
Emerging from the water removes competing current pathways, concentrating more of the discharge through the contacted threat. Repeated high-voltage volleys during brief contact can persuade an approaching predator or intruder to withdraw rapidly. Alexander von Humboldt famously described electric eels rising against horses driven into shallow South American water during an early expedition. Modern experiments confirm defensive leaping, although they cannot verify every dramatic detail preserved in Humboldt's 19th century account.
Instrumented trials confirm that climbing contact increases electrical delivery. Measured current rose as the eel climbed higher.
The same electric tissues power both predatory strikes and defensive leaps. That helps during shared organ deployment. Sax organ contributes weaker pulses used primarily for electrolocation, orientation, and communication rather than forceful attack underwater. Proteomic comparisons reveal distinct molecular profiles across the main, hunters, and sax electric organs within specialized tissues. Differences in channels, pumps, and structural proteins help each electric organ meet distinct energetic and signaling demands. Electric organs originate from muscle lineage cells during development. That process repurposes muscle precursors into non-contractile specialized electrical cells. During development, muscle precursors lose ordinary contractile machinery and gain the membrane specialization needed for electrical output. Electric organs evolved independently multiple times among fishes. Distant lineages repeatedly modified muscle through similar genetic pathways. Distant electric fish lineages repeatedly reused related genetic pathways while independently transforming muscle into electricity-producing tissue. Engineers examine electrocyte stacking for ideas about soft ion-based power sources, sensors, and bio-inspired materials today.
Bio-inspired research does not mean a living eel functions like a practical battery for ordinary human technology. Ulta's electric eels have been observed gathering in groups exceeding 100 individuals near a remote Amazonian lake.
Coordinated movement herds prey into a dense, shallow aggregation. Herding concentrates many targets within one strike zone. Most eels maintain the encircling formation, while a smaller subgroup advances toward the compressed prey school together.
Several hunters then discharge high-voltage volleys nearly simultaneously. Timing several discharges together broadens the affected prey area.
Synchronized volleys can expose, stun, and scatter many small fish concentrated inside the shallow prey aggregation simultaneously. Nearby group members exploit the brief feeding opportunity created after several hunters discharge electricity together during feeding. The sequence can repeat during a single hunting event. Repeated cycles increase feeding efficiency under exceptional conditions. Similar events recorded in different years suggest structured social predation rather than one accidental gathering over time. Local prey density may make cooperative hunting worthwhile. Dense seasonal shoals can reward brief temporary social coordination.
Cooperative hunting likely appears only where prey density, shallow water, and local geography make coordination worthwhile for multiple hunters.
Group hunting is documented in Volta's electric eel, but should not be generalized across every species, habitat, or population.
Researchers still do not know how individuals coordinate each strike. The advantage matters during group coordination mechanisms.
Weak electrical pulses, body movements, and spatial position remain plausible signals for coordinating group attacks underwater together.
Field electrode arrays could separate individual discharge patterns during group hunts. This matters during field electrode monitoring.
Synchronized measurements may reveal whether attacks are actively coordinated. Combined data can expose timing of individual roles.
Protecting electric eel behavior requires conserving connected floodplains, tributaries, and seasonal channels throughout the greater Amazon basin.
Dams, pollution, and altered flood cycles can disrupt prey movements, breeding habitat, and seasonal hunting opportunities locally.
Healthy river connectivity preserves both electric eel diversity and the ecological conditions supporting their specialized behavior regionally. Together, electrolocation, remote muscle control, hidden prey detection, curling, leaping, and social hunting reveal exceptionally precise bioelectric behavior. Electric eels are living batteries that sense, command, defend, and sometimes hunt together through carefully controlled bioelectricity. This Antarctic fish reaches adulthood without red blood cells, leaving its circulating blood pale and nearly transparent. Its entire evolutionary story unfolded within the isolated, freezing waters surrounding Antarctica. The Antarctic circumpolar current helped isolate southern fishes from warmer oceans for millions of years, supporting southern ocean separation. These seas remain cold enough to freeze the body fluids of most unprotected fishes, central to sub-zero seawater exposure. Antifreeze glycoproteins prevent dangerous ice crystals from growing inside many Antarctic nodovoid fishes, central to antifreeze crystal control. These proteins attach to ice and interrupt the repeating structure needed for further growth, supporting ice-binding molecular defense. Cold water slows biochemical reactions, movement, digestion, and nearly every other process inside the animal, supporting cold-slowed biochemistry. A comparatively low metabolic demand reduces the amount of oxygen its tissues must receive each minute, supporting reduced metabolic demand. Nearly every other vertebrate transports oxygen using red cells packed with hemoglobin, while preserving standard vertebrate oxygen transport. Hemoglobin multiplies blood's oxygen capacity by reversibly binding gas molecules inside circulating cells, which affects hemoglobin oxygen binding. Icefish blood lacks both the red cells and their dominant respiratory pigment, sustaining translucent plasma circulation throughout Antarctic activity. Under a microscope, its circulation appears strikingly different from ordinary vertebrate blood, which affects erythrocyte-free blood samples. Oxygen must travel physically dissolved within plasma rather than attached to hemoglobin, sustaining plasma-dissolved oxygen throughout Antarctic activity.
That method carries only a small fraction of the oxygen transported by red-blooded relatives, supporting weak oxygen delivery.
Losing hemoglobin reduced blood oxygen capacity by roughly an order of magnitude, with consequences for collapsed carrying capacity. Yet the fish survives because its entire circulatory system compensates for that enormous deficit, supporting whole system compensation. No single adaptation explains life without red blood. Several mechanisms work together continuously, which cold seawater naturally holds more dissolved oxygen than warm seawater, compensated by cold water oxygen abundance inside Antarctic tissues. Abundant environmental oxygen improves diffusion across the gills, despite weak transport inside the blood, which affects gill diffusion efficiency.
The Antarctic environment made a normally catastrophic blood defect temporarily survivable.
Adult crocodile icefishes are the only known vertebrates completely lacking circulating red blood cells, central to adult erythrocyte absence. Their developmental program no longer produces the mature oxygen-carrying cells typical of vertebrates, supporting arrested blood cell development. Genomic evidence records the breakdown of genes required for functional hemoglobin, compensated by globin gene degeneration inside Antarctic tissues. Key globin genes were deleted or reduced to non-functional genomic remnants, compensated by non-functional genomic remnants inside Antarctic tissues. Globin loss occurred after the icefish lineage separated from hemoglobin-producing notothenioids, while preserving post-divergence hemoglobin loss. Modern white-blooded icefishes inherited the condition from a common ancestor, compensated by shared ancestral deletion inside Antarctic tissues. The family later diversified while retaining its unusual blood physiology, compensated by icefish family diversification inside Antarctic tissues. Myoglobin followed a different evolutionary path and disappeared independently in several icefish species, which affects independent myoglobin loss. Where present, myoglobin helps buffer oxygen inside constantly active heart cells, revealing cardiac oxygen buffering under stable cold conditions. Some icefish hearts function without either hemoglobin or cardiac myoglobin, sustaining myoglobin-free heart function throughout Antarctic activity. Independent losses demonstrate that similar physiology evolved repeatedly within the family, compensated by repeated evolutionary loss inside Antarctic tissues.
Scientists still debate whether hemoglobin loss was advantageous or merely survivable under extreme cold.
Removing red cells made blood easier to pump while severely weakening oxygen transport, which affects viscosity-capacity trade-offs. Lower viscosity reduces resistance within the circulation, partly offset through low-resistance plasma flow across cold tissues. Greater cardiac output partly offset the small amount of oxygen carried per unit blood, which affects elevated cardiac output. Wide vessels allow high-volume flow without excessive pressure, partly offset through wide vessel circulation across cold tissues. Dense capillary networks shorten the distance between plasma oxygen and tissue cells, tied closely to dense capillary architecture. Mitochondrial abundance increases the cellular surface available for oxygen use, partly offset through mitochondrial oxygen use across cold tissues. Icefish mitochondria also display unusual density, size, and internal organization, partly offset through unusual mitochondrial morphology across cold tissues.
Hemoglobin loss reshaped anatomy from genes to vessels, heart, and cellular energy machinery, especially through genome-to-heart compensation.
Every delivered oxygen molecule begins as gas dissolved within the surrounding seawater, while preserving gill plasma oxygen transfer. Lower temperature increases the amount of oxygen water can hold, compensated by temperature-dependent oxygen solubility inside Antarctic tissues. Polar conditions therefore maximize the oxygen available for passive uptake, compensated by polar passive uptake inside Antarctic tissues. Thin exchange surfaces reduce the distance oxygen must diffuse, partly offset through thin membrane diffusion across cold tissues. No cellular carrier captures the gas after it enters circulation, revealing carrier-free circulation under stable cold conditions.
Carrying more plasma increases the total dissolved oxygen moving through the animal, sustaining expanded blood volume throughout Antarctic activity. Icefishes maintain substantially greater blood volume than many related fishes, partly offset through high plasma volume across cold tissues.
Cell-free blood flows with comparatively low resistance, partly offset through low cellular crowding across cold tissues.
High vascular density increases the area available for oxygen delivery, compensated by vascular oxygen delivery area inside Antarctic tissues. Short diffusion distances compensate partly for low oxygen concentration, partly offset through short tissue diffusion across cold tissues. Delivery succeeds through broad distribution rather than concentrated oxygen cargo, partly offset through distributed capillary delivery across cold tissues. Behavior also keeps oxygen demand within the circulation's restricted capacity, partly offset through behavioral oxygen conservation across cold tissues. Intense activity can challenge a system with little oxygen reserve, partly offset through burst swimming limitation across cold tissues. Icefishes generally possess limited scope for prolonged high-performance swimming, partly offset through low aerobic scope across cold tissues. Warmer conditions raise metabolic demand while lowering water's oxygen content, compensated by warming-driven oxygen mismatch inside Antarctic tissues. Temperature therefore compresses the animal's physiological safety margin from both directions, compensated by shrinking physiological margin inside Antarctic tissues. Its unusual blood works best within the environment where it evolved, compensated by stable sub-zero performance inside Antarctic tissues.
Depth and local circulation can provide relatively stable thermal conditions, compensated by deep water thermal refuge inside Antarctic tissues.
Shallow populations may encounter faster environmental change through shallow water exposure, limiting stress while sustaining water exposure.
Environmental oxygen and cardiovascular compensation remain inseparable parts of the same survival system, which affects environment circulation coupling. Icefish hearts are enlarged relative to those of similarly sized red-blooded relatives, which affects enlarged ventricular anatomy. Each beat moves an unusually large volume through the circulation, supporting high stroke volume throughout Antarctic cardiac activity. High stroke volume raises cardiac output without requiring extremely rapid heart rates, with consequences for cardiac output compensation. Cold cardiac muscle contracts slowly and depends on specialized cellular machinery, compensated by cold cardiac machinery inside Antarctic tissues. Mitochondrial density supports aerobic energy production inside the oversized heart, partly offset through heart mitochondrial density across cold tissues. Dense vessels keep oxygen pathways short within cardiac tissue, partly offset through short cardiac diffusion across cold tissues. Some species add myoglobin storage within the heart, partly offset through retained cardiac myoglobin across cold tissues. Other species survive after losing cardiac myoglobin independently, partly offset through independent myoglobin absence across cold tissues. Different lineages reach similar physiological outcomes through distinct genetic changes, partly offset through convergent cardiovascular outcomes across cold tissues.
Elevated nitric oxide signaling may help promote wide vessels and vascular growth, tied closely to nitric oxide signaling.
Nitric oxide regulates both blood flow and formation of new vessels, compensated by angiogenic vessel growth inside Antarctic tissues.
Long-term signaling can reshape anatomy throughout growth, through developmental compensation.
Vascular differences emerge as the animal develops, through heart growth trajectories, limiting stress while sustaining heart growth trajectories in Antarctica.
Static signals may transform a blood defect into a stable body plan, sustaining homeostatic circulatory remodeling throughout Antarctic activity. Low viscosity makes large volume pumping mechanically easier, partly offset through viscosity-enabled high flow across cold tissues. Tips. Cardiovascular compensation still requires substantial energy. Through energetic compensation costs, limiting
the fish pays for weak blood with a larger circulatory apparatus, revealing large circulatory investment under stable cold conditions. Warmer water can push that enlarged system toward its performance ceiling, sustaining thermal cardiac limits throughout Antarctic activity. Cardiac capacity may limit acute warming tolerance in some species, partly offset through cardiac performance ceiling across cold tissues.
Every compensation traces back to an ancient loss recorded in the genome, with consequences for integrated polar physiology. Their closest red-blooded relatives still retain that ancestral system, partly offset through retained relative physiology across cold tissues.
A major deletion destroyed essential hemoglobin coating material, partly offset through beta-globin deletion across cold tissues. Additional remnants preserve a molecular fossil of the lost pathway, compensated by alpha-globin genomic fossil inside Antarctic tissues.
Once a protein was no longer required, disabling mutations accumulated more freely, central to post-loss mutation accumulation.
Blood physiology changed far beyond the globin genes themselves, partly offset through reduced iron physiology across cold tissues.
White blood contains dramatically less iron bound in respiratory pigment, compensated by iron-poor white blood inside Antarctic tissues. The absence of red cells lowers viscosity substantially, partly offset through erythrocyte-free viscosity across cold tissues.
Lower viscosity may have softened the damage without making hemoglobin loss beneficial, sustaining evolutionary trade-off interpretation throughout Antarctic activity. Environmental conditions created a rare window in which the mutation could persist, sustaining cold ancestral tolerance throughout Antarctic activity.
Similar gene loss would be far less tolerable in warmer, oxygen-poor seas, which affects warm water incompatibility.
Red-blooded relatives often retain greater capacity for oxygen transport during thermal stress, which affects relative thermal capacity. Extreme specialization can increase success in stable environments while reducing resilience to rapid change. Supporting specialization, genome studies reveal additional adaptations beyond blood and circulation, partly offset through antioxidant gene expansion across cold tissues. Oxygen-rich water and abundant mitochondria can increase oxidative stress, partly offset through mitochondrial oxidative pressure across cold tissues. Strong antioxidant and repair systems limit damage from reactive molecules, partly offset through macromolecular repair defense across cold tissues. Icefish survival depends on a broader Antarctic molecular toolkit, partly offset through broader cold adaptation across cold tissues. Traits optimized for constant cold may become liabilities during warming, partly offset through warming-created mismatch across cold tissues.
Climate change modifies several ecological pressures simultaneously through multi-factor climate pressure.
Risk will vary among species, locations, depths, and life stages, partly offset through species-specific exposure across cold tissues. Warm water holds less dissolved oxygen while animal metabolism accelerates, partly offset through warming oxygen decline across cold tissues. Icefish face simultaneous reductions in supply and increases in demand, compensated by aerobic supply-demand compression inside Antarctic tissues.
Limited oxygen carrying capacity may bring some ice fishes to their ceiling sooner, tied closely to earlier performance ceilings. Thermal vulnerability is not identical across the family, partly offset through variable family vulnerability across cold tissues. Behavioral movement may reduce exposure to warming surface layers, partly offset through behavioral thermal refuge across cold tissues. Mutagens. Suitable cold refuges may not exist everywhere. Through geographic restraints, limiting stress, while
early life stages may encounter different thermal risks than adults, compensated by larval thermal exposure inside Antarctic tissues. Warming can reshape development before circulatory compensation is fully established, balanced through developmental oxygen stress during polar life. Changing prey fields can indirectly affect icefish energy budgets, partly offset through changing prey networks across cold tissues. Reduced food could make costly cardiovascular compensation harder to maintain, partly offset through cardiovascular energy deficit across cold tissues. Field monitoring is essential for separating short experiments from population trends, with consequences for long-term population monitoring. Collections reveal anatomy, genetics, diet, and physiological condition, partly offset through research specimen collection across cold tissues. Modern tools connect whole animal performance with molecular mechanisms, partly offset through integrated molecular analysis across cold tissues. Comparative studies identify which traits followed hemoglobin loss and which evolved earlier, with consequences for comparative evolutionary mapping. Variation within the family turns icefishes into a natural evolutionary experiment, with consequences for within-family physiological variation.
Their biology offers insights into oxygen transport without providing a direct model for human treatment, supporting biomedical research boundaries.
Genes. Understanding compensation may illuminate general principles of cardiovascular plasticity, partly offset. Those adaptations remain inseparable from the cold, oxygen-rich sea that made them possible, helping explain Southern Ocean dependence.
Its future depends on whether physiology can keep pace with changing Antarctic water, tied closely to future warming pressure.
Antarctic icefish survive without red blood by rebuilding nearly every other part of oxygen delivery, supporting integrated oxygen delivery.
This seabird can sleep while remaining airborne above the open ocean. Long flights inspired a question that behavior alone could not answer. Researchers studied breeding female great frigate birds from a Galapagos colony. A lightweight recorder was attached before each bird returned to flight.
Electrodes measured electrical activity from both brain hemispheres.
An accelerometer recorded head motion and turning forces.
A separate GPS unit tracked position and altitude.
Together, the instruments linked brain state with real flight behavior.
Some recorded journeys covered thousands of kilometers without landing. The longest sleep recordings followed birds aloft for about 10 days. Over deep water, the birds had nowhere safe to perch.
Frigate birds avoid prolonged contact with the ocean surface.
Their plumage is less waterproof than that of many seabirds.
Getting airborne after becoming soaked would be difficult. Low wing loading makes sustained soaring unusually efficient.
A deeply forked tail provides precise aerial control. At Atmospheric updrafts supply altitude without constant flapping. Circling converts rising air into height. Stored altitude then powers long descending glides.
Soaring reduces the muscular cost of staying airborne.
Direct brain recordings finally revealed whether flight contained genuine sleep. Sometimes one hemisphere entered slow-wave sleep, while the other remained more awake.
Bird vision is strongly crossed between eye and opposite hemisphere.
The awake hemisphere could monitor visual information from the open eye. During asymmetric sleep, the open eye often faced the direction of turning. Visual monitoring may help avoid collisions inside crowded rising air. Half-brain sleep preserved some vigilance during flight. Hemispheric sleep also helps other birds monitor danger on land. In frigate birds, vigilance appears linked to navigation and nearby traffic.
The hemispheres can differ in sleep depth, rather than switching completely.
Sleep exists along a continuum of hemispheric asymmetry. Frigate birds also slept with both hemispheres simultaneously. Bihemispheric sleep showed that one awake hemisphere was not always required.
Aerodynamic stability can persist through short bouts of whole brain sleep.
Updrafts reduce the need for active altitude control.
Most flight sleep occurred while birds circled in rising air.
Light provides time before a sleeping bird approaches the water.
Birds generally remained awake near the ocean surface. Foraging demands favored wakefulness during daylight. During flight, that half-brain sleep allowed rest without surrendering all visual attention. Eye state matched the turning direction during many asymmetric sleep bouts. Either hemisphere could become the deeper sleeping side. Sleep arrived in short fragments rather than long, continuous periods. Typical flight sleep bouts lasted only around 12 seconds. The longest uninterrupted episode remained under 6 minutes. Dozens of brief naps accumulated across darkness.
Sleep occupied only a small fraction of time aloft.
Recorded birds slept during less than 3% of flight.
Daily flight sleep averaged less than 1 hour.
Ecological demands kept the birds awake most of each day and night.
Frigate birds track ocean features associated with future feeding opportunities.
Following changing ocean patterns may require sustained attention.
Large predators can push prey toward the surface.
Frigate birds capture food while remaining airborne.
They sometimes harass other seabirds for food.
Kleptoparasitism provides another aerial feeding strategy.
Efficient feeding must support days of continuous movement. Aerodynamics minimize the cost of remaining aloft. Night flight involved even less flapping than daytime travel.
Despite sleeping in flight, the birds obtained remarkably little sleep.
Land sleep exceeded flight sleep by more than an order of magnitude. Back at the colony, sleep became longer and deeper. Land allowed more continuous slow-wave sleep.
Flight sleep was generally lighter than land sleep.
A secure surface removed the need for aerodynamic control.
The recorded females were returning to chicks between foraging trips.
Parental demand made long foraging journeys necessary.
Food resources could lie thousands of kilometers away.
Returning to land created an opportunity for extended sleep.
Researchers still debate how completely land sleep repays losses from flight. Available recordings do not capture every transition between sea and land. Longer studies could measure cumulative sleep recovery. New biologgers may reveal how sleep changes during longer flights.
Tracking studies show longer airborne journeys than current brain recordings cover.
Continuous flight does not automatically prove continuous in-flight sleep. Brain activity is required to identify sleep reliably. EEG distinguishes the major avian brain states.
Rare flight bouts included rapid eye movement sleep.
Brief REM did not visibly disrupt the recorded trajectory. Avian REM episodes can last only seconds. Reduced muscle tone was brief enough for flight to continue. Atmospheric support may buffer momentary reductions in active control. Several safeguards overlap during these rare episodes.
REM sleep ended rapidly.
Most sleep aloft consisted of slow-wave sleep. Both asymmetric and symmetric patterns occurred.
Sleep strongly favored circling flight.
Tension remained highest near potential feeding zones. Birds often gained height before sleeping. Flight sleep combined several strategies rather than one simple autopilot. Altitude reduced immediate danger from descent.
Thermals supplied passive support.
Hemispheric sleep, preserved directional awareness. Brief naps, limited exposure to reduced attention.
Together, these features made sleep aloft possible.
Human responses cannot be inferred directly from a seabird. How frigatebirds function on so little sleep remains unresolved.
Several physiological explanations are still under investigation.
Sleep may be regulated more locally than whole brain labels suggest. On land, the bird finally gains a stable place to rest. Both hemispheres can enter deeper sleep. Daily sleep rises to more than 12 hours. Slow wave activity becomes stronger. Adhika.
Sleep episodes become more continuous. REM sleep also occurs safely on land.
Resting conditions permit fuller sleep architecture. Land sleep likely contributes to recovery. Complete repayment of lost sleep remains uncertain. Future studies may reveal the hidden costs of oceanic sleeplessness. Other species may use different sleep strategies. Long flight alone cannot establish sleep on the wing.
Smaller instruments could expand direct tests.
New recordings may reveal multiple solutions to sleep during migration. Great frigatebirds remain the first birds directly proven to sleep in flight. Their recordings revealed several unexpected sleep states. One eye can monitor the turn while the opposite hemisphere rests.
Sometimes the entire brain sleeps while flight continues.
Yet total sleep remains astonishingly small at sea. Frigatebirds sleep in the sky by combining brief naps, soaring, and partial vigilance.
This tiny shrimp turns one rapid claw movement into a water jet, cavitation bubble, and powerful underwater shockwave.
Napping shrimps inhabit warm coastal ecosystems where sound travels efficiently through water, and visibility may remain limited.